Good evening, everyone. I'm Anup. Let's talk about linear regression. This is the pillar, this is the foundation of any analysis. This is based on ratio, proportion, and linear line means a straight line. Now, the question is, why do we prefer a linear line, a straight line, for predicting something? If you have a straight line, it makes life easier to predict something, irrespective in professional life, in your data, or even in your personal life. That is why the idea is to straighten the line of a data set for a better prediction, for a more accurate prediction. Hence, we transform the data to straighten the line, even though it is very rare when you get a data with a straight line. As the complexity of data increases, your data becomes more non-parametric. You don't get a normal data in life. Today we'll talk about linear regression, its concepts, the objective, the goal, and some of the basic, the outcome, and why they are important. We have taken a small sample set of 1124 rows with 1, 2, 3, 4, 5, 6, 7 variables, out of which overall service level is a dependent variable, what we also called Y, or the response. On the other hand, we have 1, 2, 3, 4. These are predictors or independent variables, or we call them X's. Apart from this, we have two factors: categorical data, year, and team leader. Here, year we have taken as a category and we have not converted into date. Based on this data, we'll be learning the first part of linear regression. As you see, we can see a straight line is the best fit line, and the blue dots, or the scattered ones, they are the data points around this straight line. The X, which we know is independent variable, the Y is a dependent variable. Let's talk about this term independent variable, or IV. Why are they called independent variable? So if we talk about overall service level, this is a dependent variable offered to IVR resolution, called offered, call answered. They are independent variables. It means all these four should not be correlated with each other. Whereas all these four are expected to be highly correlated with the Y. If these four are correlated, then they will not be termed as independent. Hence, we will see during the lesson if they are correlated or they are not correlated, and if they are correlated, how do we treat them? So, we'll be having a short lesson as a first part, and we'll be working on the data on RStudio. Later, when we make more videos, we'll take the same data on Python, we'll take the same data on Minitab, and we'll learn them. So let's look at the steps. Following the steps before building a model is very important. So let's first talk about the regression, as I said, which is the pillar of the foundation of any data analysis. We will learn some of the key terms, key observations, and we will learn how to interpret them. Interpreting the term, the outcome, is very, very important. What is the objective of building a linear regression model? The objective is very clear. We have to create an equation. Just give me a minute. We have to create an equation this is the objective of regression or linear regression, where we say y is equal to beta 0, which is the intercept, which we will discuss, plus beta 1 into x1 plus beta 2 into x2 plus, we will go on adding the variables, plus the error or residual, which we will learn. This is the objective of linear regression, to build a strong equation which can actually predict your y, your response. Now, why do we use regression? We are using regression to predict a number with a confidence interval. Let's understand, when we talk about prediction, we have a data set. This is my past performance or existing performance. We are trying to predict the performance of the future by bringing up new X or a new data. We have to build a model in such a way so that whenever we bring a new data and we test it, we should be able to predict with certain level of accuracy. So we always split our data when we are building a model. We split the data into train and test. We will learn how to split the data. Why do we split the data into train and test? The train data is to build a model. Train data is to build a model, while the test data is to build model. Test is to test your model. What does this mean? Based on your data, when you split into two, you are building a model, you're training your machine, you're training your model in such a way that whenever a new data set comes in or a new value comes in, it should be able to predict in line with the model that you have trained. When we are learning, when we are building a model, we split this entire data set into two parts. And universally, as a thumb rule, we take 70% as test train data, whereas we take 30% as a test data. It depends on the business. But as a thumb rule, we go with 70 to 30 ratio. Once we split the data, we keep the test data aside. We only train on the trained data, which is 70% of this data set. So now when we move to R, this is our data set. I'm not getting too much into libraries. The objective over here is not to teach you R. The objective is to teach you or guide you on linear regression. You can build the models on R, Python, Azure, any statistical platform that you prefer. We must follow some steps when we are building a linear model or a regression model. It is very important to visualize your data or do your EDA. That is the exploratory data analysis. What we do, when we have the data, the first thing we must see is the summary of your data or 5 summary point, which talks about your mean, median, IQR, minimum, maximum. That gives you a lot of idea as what the data looks like. Then you can also create a box plot to visualize the data, to visualize the outliers. Then you must also look at the histogram to look at the distribution of your data. At this moment, I'm not covering this because if you look at my video, which was uploaded yesterday, that talks very clearly about the summary of a data set or summary of a variable, which talks about the mean, median, mode, and the 5 summary point. Here I would like to go straight to the linear regression model. It is very important before building any model, you must understand the assumptions of a certain analysis. Your assumption should not be violated. You must try to validate the assumptions. In reality, all your assumptions may not be met. They will be violated to some extent. However, that does not mean we don't move with analysis. We try our best to treat the data, we try our best to transform the data, but not necessarily that always your data, whatever you try to treat, will become normal or meet all your assumptions before the analysis. If your data, if your normality comes closer, if your data set comes closer to the normality, it is good to go with analysis. If the data is not getting transformed at all, if you are very far from the normality, we suggest to discard the data. Else, your prediction, your plan of action, your business solution will not really work in the future. So what are the assumptions of a linear regression model? The first assumption is, let me show you. The first assumption is independent of observations. In linear regression, when you have several variables for multiple linear regression, they are in a random position. It should not have any autocorrelation. Unlike time series, where autocorrelation is appreciated. And we check the independence of observations, autocorrelation, by a test called Darwin-Watson test. If you run this Darwin-Watson test, on this particular data set, let's see what it gives you. It says that there is autocorrelation because the p-value at 95% confidence level is 0.02, which is less than 0.05. However, if you look at the p-value, the lowest significance level is 0.02. There is autocorrelation, but the magnitude is not very high. However, we may have to treat this. The second assumption, the variable should be independent. The variables should not have multicollinearity. And we have a test called VIF, which is called Variance Inflation Factor Test, for checking the multicollinearity. If you have to check the VIF, you have to build the linear model before testing the VIF. So the initial model with service level as your dependent variable and offered to IVR resolution, calls offered, call answered, are your predictors. And we build an initial model to check what it says. Right now, we are not checking any outcome. We are trying to see the VIF or the multicollinearity. So, under this VIF, if you run this code, you can see that all these variables, all these predictors are above VIF 5. As a thumb rule, the VIF, any VIF below 4 or below 5 states that there is no multicollinearity or this little multicollinearity, and we can accept it. However, anything above 5 may have multicollinearity, we must treat them. Here you can see 1, 2, and 3, they have high multicollinearity, whereas call answer has 5.24, we can take it on the border. So we have seen this, so this assumption also fails. The normality assumption also fails, the autocorrelation also fails. Now we move to the third assumption, the normal distribution. Your data should have a normal distribution, your Y should have a normal distribution. And we test it with Shapiro test. If we test this, here also we see that the p-value less than 0.05 if we consider 95% confidence level, so our normality also fails. So if you see overall, most of the assumptions have failed. Let's look at the linearity. Your model should be linear. So if we look at the model, if we look at the coefficient, we can see that this is a linear regression and this is a linear model. If it was not linear, there would be more than one term. It could be multiplication, it could be addition, or it could be exponential. However, we see these are one terms. It indicates that's a linear model, and this passes. Homogeneity of variance, it also says that all your variance should be equal. The variance of all the variables assumed to be equal. In order to test this assumption, we have a Levin test. When you run a Levin test, remember, it runs with a continuous data on the Y and a factor on the X. So I'm trying to see this with the team leaders and the year. With the team leaders, your p-value is 0.3. It means If we see the data, there's no significant variance amongst the scores of the team leaders. If we look at year-wise variance, we can see the F value and we can see the P value. It is more than F. Also shows that there is a year-wise variance. There's significant difference amongst the years. Hence, year-wise it fails, but team leader-wise it passes. So overall, if you look at the assumptions, all the assumptions are failing, which indicates that your data is not ready for analysis. It requires some transformation. There could be different reasons. The reasons could be some outliers. If you look at the summary, if we take the summary of I'm sorry, we have to take, let's take the summary of if you take the summary of the initial model that we have built, look at this residual. The residual has a minimum of minus 0.37 and the maximum of 0.67. This clearly indicates that there are several outliers, and this is appearing because of high variance. If you look at the median 0.008, look at the quartile 1 and look at the quartile 3, again there's a big difference and the IQR is high. It means the problem is not on quartile 1, quartile 3. The problem is towards the ends. The problem seems to be on the left hand side, because if you look at the minimum and the maximum, and that may be a reason why your normality and most of the assumptions are failing. Then what to do? This is the initial model, and the initial model the R square, which we will discuss, looks at 64%. It means all these variables together is not being able to explain the change in response or the Y. We'll see one by one why this is happening. This library LM test is for linear regression, if we look at the initial model that we have built, but before that, let me tell you, splitting the data was important. Okay, so what we had talked in the beginning, that we'll be building train data and test data. This library CA tools in R is the library which splits the data. Sets.seed is to just give a name to memorize the transaction or the code or the activity I had run, which I'm not talking detail about set.seed right now. This is the way we split the data. I've taken 70:30 ratio, and we split the data into train and test. This is my train data. Out of 1124, my train data has 643 observations with 7 variables. My test data has 481 observation, 481 rows with 7 variables. We keep the test data aside. We are working on the train data. We are not touching the test data at all. So once we build the model, we can also have a look at the correlation matrix. That gives you a visualization. You can very well see the correlation or scatter plot matrix. And you can see that this variable called offered has a strong correlation. This has a strong correlation, positive strong correlation. This does not seem to be having any correlation between the overall service level and the IVR resolution. So this actually gives you a visualization even before building a model. There are many other ways to explore the data before building any model. However, remember, assumptions are important when you're considering to build a model. So I would like to jump to the outcome or the interpretation of the report of the linear regression model that we built. There's a lot to discuss in regression. There are many concepts which we will cover in different videos and step by step. So if we look at this model, let us understand the model. You say this is a formula. We have used these variables. these predictors to predict the service level. This is a residual which we also called error. And you can see the minimum is minus 0.57, where the maximum is on the positive side of 51. This clearly indicates that there is a huge variance, and data is of course not normal, the residual is not normal, whereas IQ, this Q1, this is minus 0.03, third quartile is 0.04, again from minus to positive 0.04. Let's understand these terms. Right now we are not seeing whether my model is right or wrong. No model is right, no model is wrong. It all depends on the business. It depends on your requirement. Of course, there are some measures to check whether the model is very poor or it is acceptable. The first thing in regression, linear regression model, overall, we first see the p-value of F statistics. If this is below the significance level, in this case, at 95%, the significance level is 0.05. And it shows that this is less than 0.05. It means the model, what it says, this explains that all these variables are strongly correlated with service level. It also says that it's rejecting the null hypothesis, saying that one of the coefficient is non-zero. The null hypothesis is that all the coefficients, the estimates that we're talking about, equals 0. When we reject the null hypothesis over here, it says one of the coefficient is not 0. This is what it indicates. This is a very important measure, R square and adjusted R square. 64 adjusted R square indicates that change in response of the Y or the variation is explained by these four variables is only around 64%. These four variables together are explaining the variation in Y by only 64%, 64.3%. Is this a good model? If you look at the R square, it does not seem to be very good, but it's not bad as well. Now there could be many other reasons why it is not that good. Ideally, your R square, adjusted R square, should be around 80-85. But this does not mean that your model is not good. R square, adjusted R square, does not really explain the quality of your model. It does not give you any root cause. Let's look at these outcomes. If you look at these three asterisks, it means all the variables individually are strongly correlated with Y, which is your overall service level. Here it says 0, 3 star, 0.002, 1, and so on and so forth. Lower the p-value, which is also the lowest significance value of the significance level, it has a better distinguishing or differentiation in the null hypothesis. For instance, if you look at this, all minus 16, but this has 0.002, it means this p-value explains a better hypothesis testing than this one. Lower the significance value, better the differentiation. Even though p-value less than 0.05 indicates and we reject the null hypothesis. But lower the significance value, better the differentiation. If you look at this one, the estimate, the intercept, what is intercept? Intercept, it means when your x is 0 and y has a certain value, that is intercept. It means even when your x is 0, y will run. Even if your income is 0, there will be some expenses. That is the intercept. So if you look at this, the intercept is also significant. It means even when these 4 variables are 0, there will be some y. There will be some service level be met. So the negative ones indicates the negative, if the service level increases, this decreases. The positive one indicates the service level increases. If IBR resolution increases, your service level increases. Now, what is a coefficient? This is intercept. What is a coefficient? Coefficient means that when 1 unit of this x, this predictor, changes, when you change 1 unit of this predictor, how much change or how much response is observed in your y. This is the coefficient. This is the estimate, this is the coefficient that we are talking about. If 1 unit of call offered changes, what is the response in y? This is the response. It changes negatively. If IBR resolution increases by 1 unit, there is a change of 3.97% in your service level. What is the standard error? This standard error increases or decreases depending on your coefficient or the slope. If you see over here, this seems to have the maximum standard error. This is offered to IBR also. The objective of any model is to reduce the standard error. When you reduce this standard error, your t-value increases. This t-value is nothing but this is coefficient divided by standard error. So higher the t-value, more significant is your variable. So over here, if you see, the call answered is the most significant variable out of all 5, including the intercept. After this, you can see IBR resolution plays a very critical role in predicting the service level. This is your residual standard error. We'll talk about the degrees of freedom in our next video. The R squared is 64%, which we discussed. The adjusted R squared is 64.3, means there's not much difference between the adjusted R square and the R square. Just to inform you, R squared is taken or considered when we have only one variable, one x and one y. That is a simple linear regression. We take the adjusted R square when we have multiple variables and when we learn a multiple linear regression. This is the difference between the two. I repeat, the first thing you must see is a p-value of the f-stat. You can also see the p-value of individual variable. But if you look at only these 4 individually, it may not give you a right picture always. Fine. So we have looked at the initial model. We have seen that all are significant. But we also have to check the VIF, the multicollinearity that we talked about. So there's a library called car, and if we look at the VIF, variance inflation factor, for the model, it says 1, 2, 3, all 4 are correlated. They have multicollinearity. So we'll talk about the multicollinearity, how to treat the multicollinearity, the VIF, in our next video. Till then, please revise, do throw questions, do ask us questions, and we'll be more than happy to answer and learn from you as well. Thank you so much for your time.